Hello and welcome everyone. So today we are going to start the second part of chapter 8, double pipe heat exchanger analysis and design. So as you can see on your screen that we have a double pipe heat exchanger. So there are two configurations given here. So the one is the counter flow and another one is parallel flow. So we can see here the temperature profiles for counter and parallel flow heat exchangers. For the counter flow, the fluid enters at different ends, and for parallel flow, the fluid enters from the same end. So for so here we have given the temperature profiles. So the capital T is indicating the warm fluid temperature, small t indicating the cold fluid temperature. So this is T1 indicating inlet temperature and T2 indicating outlet temperature. And if you see the temperature variation along the length of the condenser exchanger, then you will see that the warm fluid entering at this end and its fluid temperature is going down, and the cold fluid which is entering from other end, its temperature is raised. So this is the case of counterflow arrangement. For parallel flow arrangement, both the fluids enters at the same end, so the warm fluid is temperature is going down and cold fluid temperature is going up. So these are the temperature profiles for parallel and counterflow heat exchangers. So here it is interesting to note that what is the temperature profile for condensers and evaporators. So for condensers, as we know that the warm fluid temperature remains constant, that means the warm fluid is changing its phase. So it is basically changing its phase from gaseous phase to liquid phase, and the cold fluid which is cooling this warm fluid is just raised by temperature, so the sensible heating of the cold fluid. So the fluid enters, so warm fluid enters, its temperature remains constant, only the latent heat is lost or latent heat is transferred to the cold fluid, and the cold fluid temperature is raised. So this is the temperature profile for the condenser case. For evaporator case, the cold fluid temperature remains constant, so the cold fluid basically the phase change takes place, so it changes phase from liquid phase to gaseous phase, and the warm fluid, its temperature is dropped because it's taking heat from the its temperature is dropped because it's giving heat to the cold fluid. So it was at high temperature and then the temperature is dropped at the outlet. So these are the two temperature profiles, one for condenser and one for evaporator. This is the third kind of condenser configuration, where we have a U tube inside the big diameter shell. So we call it one shell and two tube heat exchanger. So if you see the temperature profile for that, so here we are having the warm fluid entering into the shell and cold fluid entering into the tube. So the warm fluid entering from here and the exiting from here, the cold fluid is entering from here and then exiting from here. So as the cold fluid enters, so it's a case of a parallel flow, because the warm fluid is also traveling this side and the cold fluid is also traveling this side. So it's a case of parallel flow. So we have a profile like this, and when it is returning, then it's a case of counter flow. So we have the profile like this. So these are the different configurations of double pipe heat exchanger, and this is a simple example for one shell and two tube heat exchanger. Further, if you look the arrangements of the heat exchangers, so the double pipe heat exchangers can be arranged in different ways. It can be arranged in series, it can be arranged in parallel depending upon your requirement, and it can be arranged in a combination of series and parallel, like here. So what is the major use of the heat exchangers? So double pipe heat exchangers, uh, it can be used for small to medium applications, and mostly it is used for sensible cooling and heating applications, and this is small scale boiling and condensation can also be used for. So what are the advantages for double pipe heat exchanger? If you see that it's a flexible, like you can add or you can make add-on by doing a series combination and parallel combination and both. So it's a flexible, and it can be used for high pressure operations because the fluid is contained within the tube and within the outer tube, so it's safe and it's easy to maintenance. Like if you see the fabrications, it's very easy. It's just a double pipe combination with end couplings, end caps, end plates, and it's easy to and it gives basically the more uniform flow distribution. It's so what is the disadvantage for that? The disadvantage is that it's bulky and expensive per unit area. Per unit area means the per unit surface area for the heat transfer. It is a bit expensive as compared to other heat exchangers. We will see that on later on this on some slides that why is it so. So this is the basic concept for the double pipe heat exchanger design, and now when we do the analysis, then what are our assumptions when before we do the analysis? That so these are few assumptions then we will take. So the first one is that the flow in the heat exchanger is steady, the properties remains constant, and there is no phase change because we know that when there is a phase change it termed as condenser and or evaporator, and there is no heat loss. That means all the heat transfer takes place between the two fluids. So the warm fluid is giving the heat to the cold fluid, and there is no loss of heat. The overall heat transfer coefficient is constant over the entire length of heat exchanger. So the heat transfer coefficient, we are talking about the overall heat transfer coefficient, remains constant from one end to other end of the heat exchanger. So if you see the schematic of the double pipe heat exchangers, then we have an inner pipe, and then we have an outer pipe. So the inner pipe we indicate by ID, sorry, the inner diameter we indicate, the inner pipe we indicate by pipe, and the outer pipe we indicate by annulus. So we talk about the inner pipe, we always call it a pipe, and we talk about the outer pipe, we call it a annulus. So for the inner pipe we have two diameters, inner diameter of this pipe and outer diameter of this pipe. So inner diameter of the pipe and the outer diameter of the pipe. Similarly, we have for the outer annulus also, inner diameter of the annulus and outer diameter of the annulus. So when we talk about the flow inside the pipe, then what is the hydraulic diameter for this pipe, and what is the characteristic diameter of this pipe? So the hydraulic diameter of this pipe is same as the diameter. So when we calculate the Reynolds number, or when we calculate the friction Reynolds number for heat transfer calculation or friction calculation, so this diameter will work as a hydraulic diameter. But here we have annular space. For this space, what is our hydraulic diameter in this case? So for in this case, our hydraulic diameter will be based on the formula for the hydraulic diameter, that is 4 times flow area divided by the friction parameter. So the 4 times the flow area. So the flow area is the area for the annulus and subtracted by the area of the pipe. So the inner diameter, so the 4 times pi inner diameter square of the annulus minus the outer diameter square for the pipe. So this is giving us the area of this annulus space, and then divide by the friction perimeter. What is the friction perimeter? Friction perimeter is this surface, the outer surface, this is subject to the fluid friction, and this inner surface, this is subjected to the friction, right? So these two surfaces, so the perimeter of this surface and the perimeter of this surface together gives you the friction perimeter. So here we are summing up the two perimeters. So this term can be expanded into two brackets. So the one bracket will cancel out and we will have with one bracket only. So this is our hydraulic diameter in case of annular space. And remember that this is for friction. This is based on the friction perimeter. Now for the heat transfer calculation. So for the heat transfer calculation, when we see that what is the perimeter that is subjected to heat transfer. So when it comes to the heat transfer, only this surface is subjected to the heat transfer, right? Because this outer surface, it doesn't take part into the heat transfer, because the heat transfer taking place from inner fluid to outer fluids or from outer fluid to inner fluid. So only this dimension is important. So when we calculate the heat transfer perimeter, then this perimeter only we considered. So this perimeter is the pi ODP, pi ODP. So our equivalent diameter, now we call it equivalent diameter, we are not calling it hydraulic diameter. So the equivalent diameter DE is 4 times the flow area and divided by the heat transfer perimeter. So the 4 multiplied by pi by 4 and D, this area, flow area. So the flow area means IDA square minus ODP square. So this gives us the equivalent diameter. So the equivalent diameter is the characteristic diameter, and that will be used for heat transfer calculations. So before that we calculated the hydraulic diameter, so this will be used for pressure drop calculations, and remember that this will be used for heat transfer calculations. So the one is we are calling it hydraulic diameter, and other we are calling it equivalent diameter. Now we want to calculate the heat transfer coefficient for the inside heat transfer and for the outside heat transfer. So the double pipe heat exchanger carrying two fluids, one inside the pipe and one in the annulus part. So depending upon the flow, whether the flow is laminar or turbulent, we use the correlations to find out the Nusselt number first, and then from the Nusselt number we find out the heat transfer coefficient, because the Nusselt number here and the heat transfer coefficient, they are related by this relation. So depending upon the flow, first we have to check whether the flow is laminar or turbulent. So that can be checked by this expression, that if your Reynolds number is below the 2200, and remember that you need to calculate the Reynolds number by this formula, and where D means this equivalent diameter, right? So if you are calculating the Reynolds number for the annulus part, then you will use DE, and if you are calculating the Reynolds number for the pipe, then you will use D, inner diameter of the pipe. So the first of all we need to calculate the Reynolds number, and once we know that whether the flow is laminar or turbulent, then we will choose the correlation accordingly. So this is for laminar flow and this is for turbulent flow. For laminar flow we use this correlation to find out the Nusselt number and then find out the heat transfer coefficient. So this is for turbulent case. So when it is called the turbulent flow for the thermal case, so when your Reynolds number is greater than or equal to 10,000, and if it is so, then we use the turbulent flow correlation, and this is our turbulent flow correlation, and it is valid for under these conditions that L over D is greater than 60 and the Prandtl number is more than 0.7 and less than 160. So Again, like first we calculate the Reynolds number. So when we calculate the Reynolds number here, then we substitute the Reynolds number and Prandtl number here to find out the heat transfer coefficient. So the D is the characteristic diameter and K is the thermal conductivity of the fluid. So we need to use the properties. So the properties will be evaluated at mean temperature, that is the mean temperature of the fluid, that the inlet and outlet mean temperature of the fluid. Now what is the case when you don't have when you are falling in the transition regime? For example, your Reynolds number is falling in the range that is more than 2200 and less than 10,000. That means your flow is neither laminar nor turbulent. So in that case you need to interpolate between the laminar and turbulent flow. So you have to do proper interpolation to get the usable value for your problem. So these are the basic information about the heat exchanger analysis, and then in the next lecture we will continue from this point onward. Thank you.